So welcome back to the machine learning course. In the last video, we talked about the linear regression and we made an example for simple regression. Simple regression is basically when we have one uh, feature for the input and one output. And if we run the code that we wrote for simple regression again, first, we produced some synthetic data, the red points, and then we fit a simple line to this data, and we were able to produce or reproduce the coefficient and the intercept that we were used to generate those synthetic data. So that was what we did last time. But in general, we need to have some metrics to evaluate how good is our regression model. And that's what we're going to talk about in this video. So if we go back to the our supervised learning file, under the regression, we were talking about the techniques, and then we started with the linear regression. Now we want to talk about how we evaluate the models that we create. There are many metrics. I have listed three here. One is mean absolute error, MAE, and that's calculated basically calculating the difference between the predicted and the actual value of y, and sum them up, sum them the absolute value up, and divide per n. That's the mean absolute error, and it gonna tell you in an average how far is your predicted from the actual. And then there is a similar metric, mean square error, MSE, which is uh, basically the same as MAE, but the difference between the predicted and actual are squared before summed up and divided per n. And then we have the R square, and the R square basically is telling us how much of the variance of the predicted data uh, are from the are explained by the model regression model that we have. So basically, it calculates the variance of the predicted versus model, and then divide this per the variance of the 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 actual data versus the mean, and and then if this is like 0, if the model is perfectly uh, describing the data, then 0 over this value gonna be 0, and then 1 minus 0 is gonna be 1, which means the model is 100% describing the variance. As if this variance is equal or even greater than the variance of the data to the mean, uh, this value is gonna be close or even greater than 1, and then this 1 minus this gonna be closer to 0 or even minus, and that shows that our model that we use to predict is not a good model and is not describing the variance uh, at all. And that's how this is used. Is We can see it as 0 to 1 or 0% to 100%, describing the variance. And the more that R2 is closer to 1 or 100%, the model is doing better. So now let's go to our code that we have. First of all, let me add a line for the mean so we can see that what do we mean by the variance from the mean. So if I have this code added, this is gonna add a line, a red line as the mean of y to the figure that we already have. Let's run it again. And you can see that this line, the dashed uh, red line, is the mean of all these red dots, the synthetic data that we have generated. And you can see that when we calculate the variance of total, that's the distance from all these points from this mean value is used. And when we are calculating the variance from the model, is the distance from the blue line. So basically we want to calculate the variance from the blue divided per the distance, the variance from the mean line, and then 1 minus that that value. So if you look at this figure already, you can notice that the the errors, the residuals between the dots and the blue lines are generally smaller than the dots and the the mean line. So we are expecting that the variance from the model be smaller than the variance from the mean, and we are expecting to have a greater than 0 and closer to 1 R2 here. And because here we also have we use the noise normal distributed with the sigma equal to 0.5 to generate these points. We're gonna calculate the MAE and the MSE, and you can see that those values gonna fall close to the sigma. But the actual relationship, there is a formula that relate those, but this is just roughly gonna tell us that because of that noise that we added, we're gonna have this MAE and MSE for our model. Uh, so now that we describe uh, the MSE, MAE, and R2, and then we saw them on the graph that how they what we mean by those metrics. Uh, it's good to add a few line to this code to actually calculate those numbers and see what are the actual values for this example that we have. So now I'm I'm going to add these few lines to calculate the MAE, MSE, and R2 metrics. I need to import the functions that are going to help me to do the math, because I don't want to like create those functions. From the scikit-learn metrics, we can have the mean absolute, mean square error, and R2 square. And for these functions, we need to provide the y predicted and also the actual y, so they can calculate those metrics. And then I'm gonna print them. So let's run this code once more. And you can see that for the MAE, we have 0.4 roughly. For MSE, we have 0.25. And R square is showing 0.75. 67 or 67%, which is not bad, and it's showing that this model is describing portion of the variance from the mean, which means it's acceptable uh, model. So if you like math, when we have added the normal distributed noise with known sigma, here was 0.5, the sigma we choose. There's actually uh, a mathematical formula to calculate the MAE and MSE. So the MAE can be also calculated directly from sigma times root of 2 over pi, which if we calculate it's going to be around the same number, 0.399. And for the MSE, the formula we're gonna have is the sigma square, which is like roughly 0.2507 here, and sigma square is 0.25, so it matches those numbers too. But of course, if the noise is not uh, perfect normal distributed, then we cannot use those formulas, and we need to calculate them from this from the actual data. So one thing that I want to test here, and you see the effect on the metrics that we have here, is to reduce the noise or increase the noise and see how it affect this metrics. And at some point I'm gonna reduce it to very low and see that how that gonna affect this metrics. So first let's go and reduce the noise a little bit, and let's run this again. So you can see it's more focused points. The noise is reduced greatly, and you can see that our fit is much better now. And you can see that the MAE is uh, 0.08 now. The MSE is 0.01, and R2 square 98%. So so the variance of the total variance can be 98% of that can be explained by this model, and you can see in the figure that is like a very good fit right now. And that's how it's when the noise is small. Now let's go and go the other way, and let's put the sigma 1.5. Let's run it again. So now you can see that the data is much more noisy, and but still our model, because it was a normal distributed noise, like we can still find that model almost perfectly, but our mean absolute error and MSE increased a lot, and only 18% of the variance, total variance, is described by our model. As you can see that the model uh, distance to the points is much greater than the previous one. And now for the last test, let's put the sigma very low, and let's run this again, and you can see that the model is perfectly feeding the data here. because there is no noise. And let's look at the numbers. They are to the power of minus 6 and to the power of minus 10, almost 0, and our R2 is almost 100%. And you can see the accuracy of uh, detecting the original parameters of the model, the parameters that were used to generate the synthetic model.